Okay, today we're going to go through and do some troubleshooting. We have our brand new scopes. We're going to run through the operation of the scope just to get us started. This actually relates to AVT 145, troubleshooting practical projects. What I really want to go over is key ways to troubleshoot. Right now I have the circuit energized, but in reality what I need to do is start out with it de-energized. I'm going to turn off power. When we give you guys faults on our practical boards, the first thing you should do is, before you apply power, look at the schematic, look at the layout, and compare the two circuits. We give you a good circuit and a bad circuit. The key thing when you look at these circuits is, before you apply power, you may have something just shorted directly to ground, power to ground. That happens a lot, especially with new installation. This here is a 555 oscillator circuit. You look at our schematic and you remember that the 555 oscillator can be used in three different ways. Monostable circuit, astable or a free running circuit, or a bistable circuit. We hook this circuit up as an astable free running circuit, meaning when it runs, it's going to toggle back and forth, toggling the LEDs. With this circuit, before I look at it, you need to kind of understand how the circuit actually works. I'm using a 555 chip, and it's easy to troubleshoot for us because we already have, it's an 8-pin DIP, dual inline package. Those 8 pins are already labeled and kind of give us a general idea of what to look for. Obviously, pin 1 is a ground. I want to look instantly before I apply power to make sure pin 1 is actually going to ground. Pin 8, I want to make sure it's tied to VCC, that our voltage is tied in. In this case, it says 9 to 15 volts. So before I apply power, I want to make sure that I'm actually supplying 9 to 15 and not blow the circuit up. And those are two very simple checks using a voltmeter. The other checks, the discharge, control, threshold, trigger, and reset, must be checked with an oscilloscope. So we're going to set up our scope and take those measurements. So again, we're going to check our circuit using a voltmeter for our basic power source. And then I need to switch to an oscilloscope in order to see if the actual circuit's going to work for us. When I look here, also I want you to recognize a couple things. One, your VCC, your positive volts, is tied to the anode of the LED on one light. And on the other light, the cathode is tied to the ground, coming out of the same output. Our output on our chip, in one case, it's supplying power to the anode, to the ground, to turn on your light. And that's called source. It's supplying a source of power. And then on the opposite LED, LED 1, power is already there, so then it must supply a ground or a sink. We call it sink. So in this case, we're using it as a sink and source output. So we need to see if we're getting both LEDs. And if I'm not getting both LEDs, then I need to determine, am I not getting my sink or am I not getting my source? So I'm going to look at this layout real quick before I apply power, set up, and then go for it. So I look here. I'm looking at my circuit, and the obvious things I want to look for before I apply power is that pin 1, in fact, goes to ground. If you remember, pin 1 is always denoted with a dot or some kind of indication. This is always a top left also. I see on my chip, I have an indentation on the top here, showing me that this is the top. Pin 1 is always the top left. I look, pin 1, and I can follow it out, and pin 1 is in fact going to the minus bus bar, which is tied to my ground. So that looks good. The positive must go to pin 8. So pin 8, I look at pin 8 you just count wrapped around the 555 chip, most chips, most DIPs, dual inline packages. I go 1, 2, 3, 4, 5, 6, 7, and 8. So I follow 8 out, and 8 goes down the jumper to the positive bus, and I follow the positive bus, going right here, the positive to the power supply. So I am good to go. I have pin 1 and 8, and this is my bad circuit, and maybe, potentially, and I do the same thing for this circuit. Now this chip has an indentation on the top, denoting what is the top. This chip here, though, doesn't have that indentation. It simply has a dot. That dot denotes pin 1. That dot is over the top of pin 1. And again, I can look at pin 1, and I'm looking to make sure it goes to ground, and in fact it does. Pin 8 goes to power, and in fact it does. Oh, wait a minute. Yes, it does. Good, good, good. Okay, so I can apply power. However, I'm in a power supply, and my power supply, it does go there, right?
Yes, it does.
Okay, my power supply, I don't know that we can actually see that, but it's an adjustable power supply. My adjustable power supply needs to be adjusted before I apply it to my circuit. I could have positive 15 and minus 15 giving me 30 volts. Goodbye chip if I do that. So I want to set this guy up. I'm simply going to disconnect him from my board, put him following polarity, connect him up to the meter. Actually, I can just disconnect one. Be good. All right. Just hold that on there. I'm going to put on voltage DC, connect my bus, or put on my power supply, 9 volts. I don't know if you can see that. 9 volts, 8.99, good to go. I'm going to turn it back off, connect my power up to my circuit, turn on the power supply, and I am lighting. It's illuminating. The good circuit and the bad circuit. On aircraft, we're usually pretty lucky. Our maintenance manuals will specify each voltage that we should see, and sometimes it gives you the timing of the circuit. Circuit's going to oscillate every 50 milliseconds. Now, I'm using a schematic that's for the electronic world, and there's not a lot there. In the electronic world, a lot of times you compare a good circuit with a bad circuit. If I have a bad TV, I might have a good TV. If I have a bad microwave, I might have a good one. I can compare back and forth. In this case, I'm going to use my good circuit to compare with my bad circuit. The first things I said I need to do, I apply power after I looked at the components, and they looked okay. Now I'm using my senses. I'm looking for smoke, I'm smelling for smoke or burning, and I can feel the top of the chip. This is low voltage, low amperage, so obviously you don't want to fear electricity, but you do want to respect it. I'm putting my hand, and I don't feel the chip getting warm. It's very a common failure on ICs is if there is a short, they will get hot, and they will get so hot they'll burn right into my proto board. In this case, no heat. I don't have any caps exploding. Resistors aren't smoking or turning brown. They start turning brown. Looks good. First thing I want to do, I'm going to check those very things. I want to go around that chip with my meter. This is a good spot to check and see what I have. So I'm going to take my ground and I'm just going to connect this up while I troubleshoot. There we go. Making sure my circuit's still on. It is. Now I'm going to go on the good one and I'm going to compare it. I'm going to go to pin 1. It should be 0 because that's the ground side. And I see I have some slight oscillation. That's totally normal. And
The glare is on the meter now.
Glare's on the meter?
There you go. There you go.
Okay. Pin 1. Now I'm going to go to pin 8. That's the main power source coming in. Pin 8's good. So 1, ground, pin 8. And really, if I really want to know for sure, I need to use that same ground. So I'm actually going to move to that ground. I'm going to take a jumper, stick it right into pin 1 here, and I want to connect this. In fact, what I really need is a alligator clip. But for right now, I'm going to hang on to that. I'm going to go around here, and I'm going to go pin 1 to 8, and I should see. Oh, thank you, sir. There we go. Terrible. Connect that up, and now I'm in pin 1, and I want to leave it here when I troubleshoot. Because really, that is my reference. Now I can go around this the circuit. I'm going to go to pin 8, compare, and there it is, 9 volts. Good to go. Now I could look at 2, 4, 5, 6, and 7 with my meter. And if I look with my meter, you're going to see that it's going up and down, building up and down. That is normal on a 555 chip. If you remember on a 555, the way that it works, of course I supply power and ground, but then when my trigger gets to 1/3 of the volts CC, in this case it's 9 volts. So when I get to 3 volts, 1/3 of VCC, it's going to trigger. It's going to trigger and give me an output, right? That output's going to remain on until I hit the threshold voltage. The threshold voltage is always 2/3, so 6 volts. So between 3 and 6, it's going to be toggled and turned on, and when I hit the threshold, boom, it's going to discharge the capacitor that's charging my trigger. So again, I supply VCC. If I look at my trigger and my threshold are both tied here to the capacitor. That capacitor and through the resistor charges. It charges this circuit. As it charges, basically pin 8 through R1 through R2 to C1, it's going to charge and build up from nothing, from 0 volts when I turn it on. When I go from 0 to 3 volts, 1/3 VCC, 3 volts, the trigger is going to trigger. Bam! It triggers and it's going to turn on. Then my threshold, when I hit 6 volts or 2/3 VCC, it's going to turn it off. It's going to trigger and knock out, basically, when it hits a trigger, it's going to hit my discharge, pin 7. Pin 7 is going to discharge that cap to 0 again, and then it's going to start the cycle over. So it discharges, and then the cap can start charging. In the meantime, that output's changing from output, a source of voltage, 9 volts-ish, to 0 volts, ground. So it is all based on this timing circuit of R1, R2, and capacitor C1. Make sense? Mm-hmm. So we're going to now op check that. The problem with that, can I see that with the meter? Well, it's going so fast when I go to pin 2, I'm seeing my meter, I'm seeing that cap and resistor charge and discharge. That's very telling. I see 3 to 6, just like we said. 1/3 volt CC, and then 2/3. It's going to hit 6. It won't go higher than 6 because once it hits 6, it's going to discharge. So I know the chip is operating, right? Because it's building up and it's discharging, so that's good. But it's going so fast, my meter's trying to keep up. This is a pretty good meter, though. It's doing a good job. I can look at my output. My output is just going to be toggling between off and on. My meter is kind of slow. It doesn't quite get to 9 volts, and it sort of gets to 0 for a second, but I'm really watching this bar more than I am the numbers to know that, yes, it is toggling back and forth. Then, pin 4. Pin 4 is nothing more than reset. Reset is an override. Reset should be high, 9 volts. If I take reset low, if I take it to 0, I'm going to control it with that. If I take it to ground, I can control the output manually. But we don't want to do it manually. That's why we tie 8 and 4 to VCC, and it's good. Pin 5. Pin 5 is another control. Pin 5, drawn on here, shows it going to 0, nothing, which is okay. Many cases in a real circuit and control, you're going to tie the control to a capacitor and then to ground just to get rid of any fluctuations. But it's okay in the way this is wired up. Pin 6 is my threshold. Remember, pin 6 and pin 2 are tied together, monitoring the output of the capacitor. So pin 6 and 2, I should see the exact same operation. I should see 3 to 6 volts. It's simply monitoring that input to demand a trigger. If I go to 7, I can watch the trigger. Go to 7, I'm watching the trigger. It's doing this, just like we said, it's going to supply 0 volts to discharge that cap. I'm looking full charge of the cap, and then 0. Full charge, bleeding it down, 0. And you can see it's happening so fast, I can't really, I need a scope to really see the big picture. And then finally, 8 was VCC. I got full voltage. So that is with my meter. I can, that's how I'm going to actually record. I'm going to record what I saw, 3 to 6, In fact, can I get something to write with later before I'll probably forget? Just throw me that pen. All right, safety first. All right. So now I can look and draw on my schematic, pin 2 and 6. What I want to see here, I'm going to actually just write this. Pin 1, 0 volts. Pin 2 and 6, I saw 3 to about 6 volts toggling. Then pin 3, I saw 0 to about 8 volts DC. Pin 4, 8 volts DC. Pin 5, nada. Pin 6, I had same as 2, so that same as 2. 7, toggling between 0 and full volts. And then 8 was 8 volts, or 9 volts DC. So that is how I'm going to compare my good and bad circuit. You just simply record it, boom, you're good. And now I want to look with my scope. With my scope, I need to set my scope up so I can see what's actually happening. When I use a scope, I need to tie this same ground, I need to tie it to pin 1 also. So what I'm going to do is move this over here, remove my meter, tie it to pin 1, and then on my scope, I want to be very careful so I don't short anything out. I just connected it to a jumper. I'm actually going to go to pin 2 there, and I'm going to start here, pin 2, and I'm going to set up my scope. When I set up my scope, there are new scopes, there's an auto feature here. That auto feature will mess you up, right? If you hit auto, which I won't yet, but when I hit auto, it'll look for signals and then call whatever it sees at that moment in time good. Really what you need to do is monitor channel 1 and 2 to make sure they're always comparing apples with apples. They must be the exact same. When I change my scale for time, that is going to do channel 1 and 2 at the same time. First things first, when I'm testing electronics, I need to be in the 10 by scale. You get the 1x and 10x. 1x will definitely load down circuits. So if I go to 10x, select 10x, then select on here the correct coupling. Channel 1, I'm going to select channel 1, which is my yellow. Channel 1, I'm making sure for 1 it's on AC coupling. AC coupling, what it does for me, I'm looking for AC. It'll keep the image centered in the middle of the scale. If I select DC, it's going to jump up however many graticules of DC are riding on this circuit. So if you have DC selected, it's going to jump up and you might have to chase it a little bit. That's okay if that's what you're looking for. Right now I'm just looking to compare signals. So AC, and then on my probe, I can select 10x. So I got AC, 10x, and it matches 10x. I'm good. Channel 1. Now I want channel 2. So I'm going to go channel 2, AC coupling, 10x. If it was, let's say it wasn't 10x, I would just simply toggle the button until I came around, because it can be 1,000 times the signal, but I'm going to bring it back to 10. What all that does, 10, is give me a good impedance matching so I don't load down the circuit. Or I shouldn't say impedance matching, but it just doesn't load down the circuit. So now I have the right settings here. Now I'm going to hit auto and you can see what's going to happen. I hit auto and it's searching for whatever signal it can find. And it found something, right? But I want to see channel 2. Turned off channel 1. That's one thing it can do, right? It didn't see something it didn't like on channel 1, so it just erased it. We don't want that. We want to compare apples with apples. So I'm going to turn channel 1 on, where this says 100 millivolts and 50 millivolts. Well, they both need to be exactly the same setting. So I need to manually turn the scale until they both say 100. And I can compare my yellow on my bad circuit to my blue on my good. Now it's jumping around quite a bit. So I can change my frequency here, and there's a time delay. When I turn the scale, you gotta turn it and pause it. If you're an old school guy like me, I kind of like the old meters better because they're instantaneous. With these, they're converting a signal, it takes a little time for it to think. So now I'm looking at the signal, but I'm still not real sure what I'm looking at. So I'm gonna scale all the way back to see what it looks like, see if I get a better glimpse. Oh, I like that a little better. I can see the charge and discharge time of the capacitor. So I'm going to scale a little bit more out. Time delay, time delay, time delay. And that's what I want. I want to see 2 or 3 2 or 3 charges and discharges. This is very nice. Okay, it's a little rough around the edges, but this is a very fast oscilloscope picking this up. So I can see the charge and discharge time of my capacitor. Remember I said it's going to build up to 1/3, right? 1/3 voltage. Then it's going to hit 2/3, and it's going to maintain and then discharge. 1/3 to 2/3, maintain, discharge, right? So that's my capacitor and resistor. It's operating. Now I look at, it's completely obvious with the scope. When I go into channel 2, there's nothing happening. Channel 2 is completely dead. And we'll get into that later. But those are really the basics of troubleshooting. How you can look at it with the meter, and the meter was kind of, I wasn't really sure what I had. And with the scope, it tells me quite a bit more information.